Integration of rational polynomials. Just a little bit about a polynomial. A polynomial is when you have a row of powers of x. Here's a simple row of powers of x. It's just got power 1 here with a constant at the end. So you could have 3x squared plus 2x minus 5, which we think of as a quadratic, but that really is a polynomial because it's got a series of powers of x, linear combinations of, and a constant at the end, or could be a 0 of course. And then the polynomial, the degree is the highest power of x, so this is a polynomial of degree 2. So the examples in the notes are here to illustrate that. This is a polynomial, isn't it? Because it's got a power 1 there, x to the 1 of course, and that's a polynomial of degree 1. This is a polynomial because it's a cubic, highest power is 3. It's a polynomial of degree 3. So that's what we've got there. And so let's have a look at some rational polynomials. That means one rational function. Rational polynomial is another way to talk about it. These are rationals because these numbers are integers or fractions. So the coefficients, the numbers of the x powers, are rationals or integers, and we call them rational polynomials. So when you've got one over the other, both are polynomials, you've basically got a rational polynomial, a fraction polynomial sort of thing, one polynomial over another. The order of the polynomial, basically, if you look at the order of the top and the order of the bottom, this is of order 1, the highest power, this is of order 2. So that corresponds to an improper rational function, polynomial function, because the power on top is bigger than or equal to the power underneath. Here the power on the top is 1, power underneath is 1, isn't it? So if you think about that as a fraction, the corresponding fraction would be of that nature, and that's an improper fraction, isn't it? So we would talk about these as improper rational polynomials because of the way the powers tell us. Okay, so these are a couple of little examples here, first of all, that we don't have to use partial fractions, because we're going to go on to talk about partial fractions in a bit, but these methods, there's certain little tricks you can do where you don't have to use partial fractions. For example here, when you got this, if I said 3 plus 4 over 9, you could split the fraction up. And sometimes it's easy to deal with problems. When it's easy to split the fraction up, that's exactly what we do. So in an example like this, we split the fraction up. So like 3 plus 4 over 9 is 3 over 9 plus 4 over 9. This would be the same in process. So it would be the first term over what's underneath plus the second term, which is minus 2, over what's underneath. Still the integral of course. But that's what we're dealing with here. This is just x, isn't it? So I'm going to scratch that now and just an x cancels top and bottom, and that leaves an x. So we can write down the answer as x squared raised to the power by 1, divide by that number, minus 2, lots of 1 over x, so that's ln x, plus k. This one is slightly different. We can't split the fraction up easily, but what we can do is we can do a little cheat method. So if I had 5 over 6, say, I could actually write that as 6 minus 1 over 6, couldn't I? And that would enable me to write it as 1 minus 1 over 6. Agreed? 5 6 is 1 minus 1 over 6. And in the same way you do, a little trick there enables us to do the integration. Because we can't do the integration here, but this, if we do this trick, we might be able to integrate it. So let's just add 1 and take 1 away then. On top, so we're adding 0, so we're not changing the problem. But now we can split it up into the first term over what's underneath, plus the second term over what's underneath. Okay, good. Now this is x plus 1 over x plus 1, so that's our 1 there, isn't it? That's why we did it. So we could get a 1 there, and that's easy to integrate. And this is actually a standard integral as well. So we can write down the answer then. This integrates to x. This is ln x plus 1 when we look in the table. Standard integrals plus a constant of integration. So it enables us to integrate it. And there's the answer there. X minus ln x ln of x plus 1 plus k. Just tidy up a bit, that's better. Okay, good. So that's that then. Now, so there's the comment there. So partial fractions. Well, if you do the algebra here, cross multiply this to get a common denominator. 3 of these, 4 of these over the product of what's underneath. Just as you would do with fractions, you'll end up with, when you expand the bracket, you've got 7x plus 10 on top, and you've got these brackets underneath. So that's how you consolidate two fractions. The reverse process is called using partial fractions. If we had this as an integral, if we did partial fractions, we'd have this problem as an integral, and we know these two integrals from previous work we've done. These are standard integrals. And the same goes for this. If you did partial fractions on this, you'd end up with this, cross multiplying the fraction. And the reverse, you can't integrate that straight away, but if you wrote it as this, all these are very easy to integrate. So basically, what we're trying to say is by using partial fractions, we can often be able to integrate awkward-looking rational polynomial functions. We're going to look at linear factors. So here's our first example then. We're going to look at this one and try and work out the partial fraction. So we're looking at linear factors, and that's the only partial fractions we're going to consider. So that would be like case 1 here. These are linear factors here and here underneath. That's linear, and that's a linear factor. That's what we say. So here we've got two linear factors, and in that case you write a over the first plus b over the second. And that's what you do. Now, how do you find a and b doing this reverse process then? Well, you multiply by the denominator first, and you write x minus 4 then, multiplying by that denominator, and then it'll be a times the x plus 3, because the x's will cancel, and then b times the x. So you basically cross multiply, and the denominator goes because you've multiplied by it. Now, to find a and b in this problem then, you either equate powers of x here, or you substitute convenient values. So the number of x's on this side will equal the number of x's on that side. Number of x squareds on this side must equal the number of x squareds on that side, if there are any, and the number of constants on this side must equal the number of constants on that side. Most times this is the preferred method, substitute convenient values. So let's put in a convenient value. To make a disappear, we can put minus 3, can't we? To make b disappear, we'll put 0. So let's try x equals 0, which is the same as equating constants in this previous method here. So put x as 0 in, we get minus 4 on this side. 0 in here, we get 3a. 0 in here, we get 0b as 0. So we can see that a is equal to minus 4/3. Now if we put in x equals minus 3 then, what will we get? Minus 3 minus 4 is minus 7 on this side. This will disappear, that's why we're doing it, and we get minus 3b. Okay, so that tells us then that b is equal to 7/3, isn't it? Minus over a minus is a plus, so we get 7/3. Okay, so basically we've got a and b. So what have we got then? We've got this x minus 4 over x plus 3 is equal to a, which is minus 4 over 3x plus b, 7/3 over the x plus 3, isn't it? So by looking at that integral, if you had that integral as a problem, it would be the integral of this and that, which we've done these before. Okay. Just a little bit of bookwork then before we do the examples. Note that 1 over, just as a reminder, ax plus b dx, as a standard integral, it's equal to the log of ax plus b, 1 over a, plus our constant of integration. So this is what we're going to use when we integrate these sorts of things here, this bit of the bookwork for integration. So let's look at the first example then. I'll scratch all this and we'll do the first example. Alright, here's our first problem. So here we need to use a method of partial fractions, don't we, to split up this rational polynomial function. So it's equal to a over the first one, plus b over the second one. It's a proper rational function because the top part's of order 1 and the highest power underneath is of order 2. So that allows us to use the method of partial fractions. So there's no problem there using this method. So multiplied by the denominator all the way through gives 3x minus 1 then on this side, cross multiply, plus bx. Now substitute convenient values. So x equals 0, minus 1 here, minus a, and 0b. So a will be 1, won't it? We put in the other value. The other convenient value is x is 1, isn't it here? This will disappear. 3 minus 1 is 2. 1 minus 1 is 0, that goes, that's why we're doing it, and we get b. So b equals 2. So we can write I, then our integral is equal to, and instead of this stuff here we can write a, which is 1, plus b, which is 2, over x minus 1 equals, now don't forget that the integral of 1 over ax plus b, remember? We wrote this down just a moment ago, is equal to ln ax plus b, 1 over a plus k. That we can use any time we want. So here this is just a standard integral log x plus 2 lots of, and this would be, here a would be 1, b would be minus 1, so it's 1 over 1, 1 minus one of those. Okay, so we get 2 lots of then, 1 over x minus 1 integrates to 1 over 1, ln x minus 1, isn't it? Here, plus k at the end. And there's our answer. So they're not too bad at the end of the day. Okay, good. Next one then. Let's scratch this now and we'll do the next one. Here's the next example then. It's a definite integral, which we'll work out in a bit. But here's the integrand. It's a rational function because it's of order 1 on top, and the highest power is of order 2, isn't it, from the x squared underneath. So it's a proper partial fraction. And it's a rational polynomial, which is a proper partial fraction. So we use this method here. So we write a over the first linear factor plus b over the second linear factor, multiplied by the denominator then. So this is just a standard thing to write. And we get this, cross multiply. Okay, we get that. Substitute convenient values now. So I've just cross multiplied and multiplied by the denominator. So that goes from underneath here and here. Now x is 2 and x is minus 1. So if we put 2 in then, 2 minus 8 is minus 6. 2 in here will disappear, that's why we're doing it. 2 plus 1 is 3, we get 3b. Minus 6 over 3 is minus 2, isn't it? So that's b. Now we'll put in x as minus 1. We get minus 9, don't we? Minus 1 minus another 2 is minus 3a. And this goes to 0. So a is minus 9 over minus 3. Minus over a minus is a plus. 9 over 3 is 3. So I will equal then the integral between 3 and 4 of this, which is just the same as writing this. A, which is 3, over x plus 1. Plus b, which is minus 2 over x minus 2 dx. Okay, so we integrate then, we get 3 ln x plus 1. This is 1 over x plus 1, which differentiates to this, integrates to this rather, minus 2 ln x minus 2, which integrates to that. It's a definite integral, so we don't put plus k, 3 and 4. Which equals, it's going to be the top value minus the bottom value. Because we're running out of time on this vid, I've just put in the top value here and the bottom value